we will meet the exchange property from this set and A. First set consists of one element, second consists of three elements.
And one question, we can add only one element to the
Yes, it
A.
suffices to find just one extension, not necessarily all possible extensions. It's enough to add for example, and this question will be solved. And after that,
If the
ask, please ask.
if the question was like the maximum number of the independent sets, if we had 4 as A and for B we had, for example, 1, 2, 3. Now we should add 4, 1, 4, 2, 4, 3, and then should we add 4, 1, 2, or no? We should just add one x to A union with only one x, or we can have x1 and x2, like 4, 1, 2.
We try to construct minimum in the minimum subset system. Of course,
Okay.
we can meet this condition by considering all subsets of S. This is obviously a majority if we consider all subsets to be an independent set. But we would like to have a minimum subset system which includes A and B. And based on this, we would like to construct the smallest extension from A and B using hereditary and exchange properties. So firstly, we should extend 4 by one of elements belonging to A. Suppose it is 1, and adding 1 4, we will meet the exchange property for one set consisting of 4 and second one consisting of 1, 2, and 3. Then we need to look what else we have to add in our subset system. So we have 1 and 4, and we have 1, 2, 3. These are two subsets of different sizes. So 1, 4 should be extended by adding either 2 or 3. And suppose we add 2, so we need to have also 1, 4, and 2. This is necessary to meet exchange property for one set which consists of 1 and 4, and second which consists of 1, 2, 3. So 1, 4 should be extended by at least one element belonging to A. This can be either 2 or 3. Suppose it is 2, and we include also this set in our subset system. Then we need to look whether we have to add something else or it suffices, and so on. So we stop our construction when no other set needed to add to our subset system. So the problem is how to construct minimum subset system which includes A and B. Maximum subset system is one which consists of all subsets of ground set. Other questions?
Can we also take a look at B and C?
B and C?
Mhm.
Yes. In subproblem B, we have a partition of S into some disjoint sets, S1, S2, and so on. Then we consider subset system S. Ground set is defined. Initially, we have some partition of S into disjoint sets. This is such a partition. Then we construct a subset system, ground set of which is S, or union of S1, S2, and so on, Sk. And after that, we say that I is constructed by taking at most one element from each subset. So we choose at most one representative from each set, and this way we construct a subset which we include in our subset system. And we need to prove that subset system defined In this way will be a matroid or will meet matroid properties. The first property is hereditary property, HP. This property means that we have a subset belonging to I, an element belonging to I, any subset of this set will also be an element from I. Why it is so? If we have some selection from this disjoint sets, so each element from I is some selection. We need to choose at most one element from each subset. So if we have some proper selection, any subset of this selection will again be a proper selection because we again choose at most one element in every subset. So it is obvious that hereditary property holds. Second property is exchange property. This property means that if we have two selections, for example A and B, so that size of A is strictly less than size of B, we can extend A by adding element from B. What does it mean that size of A is less than size of B? It means that selection A consists of lesser number of elements than compared with selection B. In that case, we obviously can. This means that we have a set from which we get an element and include it in B, but we have no representative from this subset which is included in A. So A can be extended by taking this representative. So the fact that selection A is less than selection B means that we have at least one subset from which we take an element and include it in B, but we have no representative in this subset which is included in A. So A can be extended by choosing this representative which was taken when we constructed V. So this is how to justify that our subset system will be a matroid. This is like choosing a literal from conjunctive normal form. When we have a formula which is represented in conjunctive normal form, we have a conjunction of several disjunctions, and there is a true assignment for this formula if and only when we choose at least one literal from each disjunction, so that our selection is consistent, meaning that we have no literal in our selection, which is a negation of others. As about subproblem C, here we have two subset systems, S1 and I1 and I2, or M1 and M2 are two matroids with disjoint ground sets. So this is first ground system, this is second ground set, S1 and S2, and we assume that intersection is empty. Then we construct a new subset system by saying that ground set is Cartesian product of S1 and S2. Or in other words, we take all pairs of elements, first of which belongs to S1, second belongs to S2. This is ground set, and then we define the subsets of S by taking a subset from I1 another subset from I2 and constructing Cartesian product of x1 and x2. So we actually have some subset system. We have a ground set and we have a set of subsets of S. And we need to check whether matroid properties satisfy. For that we need to choose hereditary property and exchange property. And let's choose that, for example, hereditary property does not have. Let's turn backward. So suppose our subset system is constructed in the following way. S1 consists of A and B. S2 consists of, for example, 0 and 1. Then we need to define a matroid structure on these ground sets. So we need to have a proper subset system. Let's consider empty and consider A and also consider B. So we take all subsets except entire set, entire S1. This is I1. In second case, I don't know, let's postpone definition of I2. In our matroid, ground set is Cartesian product of S1 and S2. It means that we need to get all possible pairs of elements taken from S1 and S2. Suppose A together with 0, A together with 1, B together with 0, and B together with 1. So this is ground set, meaning that we take all combinations of elements from our sets. Let's include in second subset system, for example, empty and just 0. And according to our construction, we need to include in I all possible combinations when we have an element x1 from I1, x from I1, or x1 from I1, and x2 from I2, and then we need to construct Cartesian product of x1 and x2. So this way we construct our subset system, and we need to show that this way we not necessarily will meet generally both of our properties. That is hereditary property and exchange property. By hereditary property, it means that we have something like this, some, something like this, and some subset belonging to this Cartesian product, we need to show that not necessarily this subset can be represented as Cartesian product of these two sets. Now suppose we choose x1 equal to a and b. A and b should be included in our system. And x2 let's choose equal to 0. So as a result, we get a together with 0. A together with 0 and B together with 0. In this case, subset will also can be represented in this way. Maybe we need to choose A together with 0. Did you solve this problem or not? Because we need to try some opportunities to get a contradiction with our assumptions.
No, unfortunately, I couldn't solve it.
Okay, let's try to find another example. A together with 0.
Mr. Kostanyan,
Oh, listen.
these are independent sets A0 and B1.
We need to choose something like this, x1 and I1. This first one is from our ground set of first matroid, second one is from ground set of second matroid. After that, we need to choose that some subset of x1 and x2 cannot be represented as a Cartesian product, despite the fact that, for example, suppose A is some subset of x1 multiplied by x2, but A cannot be represented as Cartesian product. For that, we need to have, for example, A together with 0. A0, A1, and B1. And subset which consists of, for example, A0 and B1 cannot be represented as Cartesian product of some subsets, first of which is from x1 and second of which is from x2. So we need to have in first matroid A and B, in second matroid 0 and 1. Okay, let's define first matroid to be all subsets of A and B, and second matroid to be all subsets of 0 and 1. And after that, we have, for example, this set A and B multiplied by 0 and 1, S1. So suppose S1 is A and B, S2 is 0 and 1. S1 is A and B, S2 is 0 and 1. This is some subset belonging to our Cartesian product. Suppose it is A. We choose A together with 0 and B together with A together with 0 and B together with 1. So A is a subset of S1 multiplied by S2. But this set cannot be represented as a Cartesian product. A0 and B with 1 cannot be represented as a Cartesian product because we need to have A and B from one side and we need to have 0 and 1 from another side. And after that, we need to consider all combinations when A is taken together with 0 and 1 and B is taken together with 0 and 1. So this subset cannot be represented as Cartesian product. So that hereditary property does not hold. Let's repeat once more. We define first matroid to be S1 I1 when S1 consists of A and B. Second matroid is S2 I2 when S2 consists of 0 and 1. And we consider all combinations of elements in I1 and I2. So these are two matroids, and we have all possible subsets of ground set. After that, we consider the following subset of the set S1 multiplied by S2. S1 multiplied by S2 is an independent set, and we choose some subset of this independent set by saying that we take A together with 0 and B together with 1, except this. Only these two elements we include in A. And we need to prove that A is again an independent set. But for that we need to prove that A can be represented as multiplication of two independent sets, x1 and x2. But it is not so. We cannot represent A together with 0 and B together with 1 as a product of x1 and x2. Why? Because we need to have as a first component either A and B, and as a second component either 0 and 1, but in that case we need to include all other combinations as well. So this subset cannot be represented as Cartesian product of two subsets from first and second matrices, and that is why hereditary property does not hold. Any questions?
Mr. Koseman, can we also take a look at NP completeness homework?
Yes, this is homework related to NP completeness, and
Yes, and the last three homeworks are not checked yet. When they will be checked, because maybe we've made a mistake and we want to learn from our mistakes. But
let's consider solutions to some of problems in this homework.
okay.
Which one would you like? What about first problem? Did you
Yes,
solve this problem?
yeah, I tried to solve it, but I don't know if it's correct or not. But I came up with some solution. If you want, I can explain it.
Okay, let's consider how to solve it. So firstly, we need to, this is our initial formula, f depending on x1, x2, and xn. So we can substitute x1 equal to 1, and suppose as a result we get formula f1, which consists of n minus 1 variables, fx2 and so on xn, and f0, which let's switch blackboard to consider this problem. So this is our initial formula, f, which consists of x1, x2, and so on xn. not, and our initialization of variables provides a true assignment for our formula. For example, suppose our formula is this one, negation x together with y and also z. This is first disjunction. This is second disjunction. And this is third disjunction. Y, for example, negation y together with z. So F consists of three disjunctions. This is D1, this is D2, and this is D3. So we need to find the true assignment for this formula, or in other words, we need to find the consistent selection from this set of literals, D1, D2, and D3. So following to our method, we consider formula F0. In F0, we assume that x is equal to 0. As a result, we get the following formula. If we substitute x equal to 0, this disjunction evaluates to 1. This disjunction becomes negation of z, and third disjunction remains the same, negation of y, disjunction z. This is our formula F0. In case when x is equal to 1, we get formula F1, which looks like this. If x is 1, negation of x is 0, so we have y disjunction z. Then we have 1. The second disjunction evaluates to 1. And third disjunction remains the same, negation y and z. This is F1. Then we ask our oracle whether F0 has a true assignment. If yes, we continue with F0. If no, we need to ask whether F1 has a true assignment. Suppose we ask about formula F0 and we get